This is chapter 20, 20.1, section 20.1. This is all about oxidation states, and you know oxidation states as, well, first of all, it's electrochemical reactions. So in electrochemical reactions, we're talking about electrons. Electrons are transferred from one species to another. Species simply meaning an ion, typically, or sometimes an atom within, like Zn here would be an atom because it doesn't have a charge, and H plus here would be an ion because it does have a charge, or a difference in electrons from the number of protons. So in order to keep track of what's lost and what's gained, we assign oxidation numbers. Now if you take a look at the equation here, you can see that zinc has an oxidation state of 0. That's what it says here. Hydrogen has a +1, so oxidation number is the same thing as valence, which is the same thing as charge. We use all of these same words: oxidation state, oxidation number, valence, and charge all basically mean the same thing. Okay, so I'm going to show you first of all how can you tell what the oxidation number is for a species, which means atom or ion, in a chemical equation. And notice that what I have here is not HCl. What I have is H plus, which means that I'm dealing with mostly net ionic equations. Okay, blast from the past. Moving on. So whether it's an atom or an ion is oxidized when it loses electrons. Now here's how I think of it. If I have a number line, you guys know what a number line looks like, and I got 0, 1, 2, and so on. When I have, and this would of course be a +1, +2, this would be a -1. What if I have something like zinc that goes from a 0 here before the reaction, and then after the reaction it goes to a +2? That is losing, oh boy, losing electrons, which means it's getting more positive. So oxidation is getting more positive. Okay, that's what it means. So zinc loses 2 electrons. It goes from neutral, or a charge or an oxidation number of 0, to a +2 ion. Okay, so notice that when we get reduced, that means that in my number line here, that if I'm going from a +1 like hydrogen is here, and it goes to 0, okay, that's the 0 right here, that means it's gaining electrons. So when something is reduced when it gets more negative. More negative is reduced, more positive is oxidized. Okay, moving on. What's reduced is the oxidizing agent, and what is oxidized is the reducing agent. It's like they switch it. So zinc, because it gets oxidized, is the reducing agent. I know that that's silly, but that's what they say. So hydrogen here, of course, because it gets reduced, is the oxidizing agent. So Ra and Oa, so I don't have to write the words out the whole time. Moving on. Okay, now here's where the bulk of the notes that you're going to have. Elements in their elemental form have an oxidation number of 0. So that would be like zinc on the left-hand side of the equation. That's parentheses, I don't know what that is. And H2 on the right-hand side of the equation. These are all O2 because of Brinkelhoff, of course. And anything that is like maybe sodium metal. Okay, so these things are all, they all have an oxidation number of 0, a charge of 0. The oxidation number of a monatomic ion is the same as its charge. So that means that number 2 is the thing we're going to use the most, because we're used to seeing elements with a charge, and these ions here like this, the charge is the oxidation number. So the oxidation number for sodium there is a +1. It's really that simple. Number 3 is nonmetals tend to have negative oxidation numbers, although some are positive in certain compounds or ions. What are we talking about? Oxygen has a -2 99% of the time unless it's peroxide. Peroxide looks like this. Well, first of all, regular oxygen exists as O with a -2, like that, whereas oxygen like this would have 0. It doesn't matter what the number is, like the Brinkelhoff number for that is 2. What if I had sulfur? I should have done this in the previous slide. Sulfur can combine in 8. The oxidation number would still be 0. Okay, so here's a case where you have peroxide. Oxygen still has a -2, but there are 2 oxygens. That's a case where there's peroxide, and each of those oxygens would have an oxidation number of 1. Hydrogen is a -1 when bonded to a metal and a +1 when bonded to a non-metal. Okay, so you may see something like this where you have sodium hydride. Okay, sodium hydride, in this case, hydride has a -1 oxidation number. Non-metals tend to have negative oxidation numbers, and this is the same. Okay, so this is the same number 3, but there's more points to it. Fluorine always has an oxidation number of either -1 or 0. So this would be 0 here, or -1. Fluorine doesn't do the other stuff because it's the most electronegative. It always pulls an electron to get an ion. Other halogens have oxidation numbers of -1 when they're negative, and they can have positive oxidation numbers, especially when they're in oxyanions. An oxyanion is just simply a way to say that they're in a polyatomic ion, such as ClO4, like this, with a -1 charge. This is perchlorate. Okay, what do we know about oxygen? Oxygen is a -2, which means this whole thing here is a -8 total for oxygen. Okay, and I'm going to find out what the charge is of chlorine. Chlorine here must have a charge of a +7 to make this math equation correct. So the whole charge of the polyatomic ion is a -1, and since there are 4 oxygens, that times a -2, I get a -8, so the +7 must be chlorine, because when I add +7 plus a -8, I get a -1. Okay, and we'll do more practicing like that. So the sum of the oxidation numbers for a neutral compound is 0, such as NaCl. That's a +1 and a -1. If we add them together, we get 0. But the sum of oxidation numbers of a polyatomic ion is the charge of the polyatomic ion, such as something like NO3. We know this as nitrate. So nitrate, when I scroll down here to do the same thing, oxygen always has a -2. Times a 3 is a -6, so I multiply the subscript times the charge. I know I'm talking fast. See if you can keep up. That means nitrogen here, there's only 1 nitrogen, and that nitrogen must have a +5, because that's what makes the math sentence correct. +5 plus a -6 equals a -1. Okay, so that's how you do oxidation numbers within a polyatomic ion. Okay, these are just example problems. I'm going to do these 2 and stop. So what is the oxidation state of chlorine in the following reaction? Here it's 0, okay, on one side, and then it goes to, now here you have OCl, and the whole thing has a -1 charge, which means that if I have a -2 here, that means this chlorine must be a +1, because that's the only way that we can get this to equal a -1. Yet over here, because of rule number 2, chlorine has a -1 oxidation number there, because it has the minus, it's a monatomic ion with a -1. But over here, it has a +1, because oxygen has a -2, and the whole thing has a -1. I know that's confusing, but that's what it looks like. What are the oxidation states of Cl and Br in the following reaction? Here it's 0. Okay, here it's a -1, because here we have a neutral compound, and potassium has a +1, which means bromine has a -1. Over here we have a neutral compound. Potassium still has a +1, and chlorine has a -1, and bromine here would be 0. Okay, I went through that pretty quickly. That's just to save some time. Rewatch it and ask questions in class, or message me. All right, I'll talk to you later.